and then misalignment, which can make axions. So we're going to start very close to the WIMP and then move further and further from it. Okay. Oh, and I forgot, I wanted to say before I jumped in, if anybody wants, I'm going to regret this, I think, but if anybody wants to wake up at sunrise and run up the mountain on Thursday morning, then you can join me and we'll meet maybe by the coffee at 6. Well, talk to me, we'll refine that and watch the weather. So Thursday we'll just run up. Okay. With whatever speed people want.
Where do we meet?
By the espresso machine in this building. Say we leave at 6. Okay. Yeah, we can run any speeds greater, less than or equal to my speed. Okay. So, yeah, actually, before I even jump in, I'm just going to say some basic things, and these things are going to completely overlap things that Anne has and will explain better than me. But just, I feel like saying them too. Okay. Some basic facts. Okay, evidence actually Anne's going to talk about tomorrow. I think that wasn't today yet. Which means I get to say it first, and then she'll say it better. But I'll just emphasize we have evidence for dark matter on multiple length scales from a diverse set of systems. So sort of famously, the rotation curves of galaxies. So you see how fast stars are moving. They're moving too fast if there weren't dark matter. There's mergers of clusters, like the famous bullet cluster image, where we can use gravitational lensing and see where the dark matter is. And then there's the CMB. And these are all probing sort of different length scales, very roughly speaking. I would say this is about 10 kiloparsec. This is maybe megaparsec. Yes, how big was the universe in the CMB formed? Actually, it's not too different from that number, but say 100 kiloparsec. These two are the easiest to explain. This is the one where we really precisely extract the amount of dark matter, and that gives us the number that we're going to be targeting with these production mechanisms I'm going to discuss, reducing the amount of energy density. And let me also just review the energy budget. Fraction of energy as we measure it today. And I'll just go in descending order. So the biggest is the cosmological constant. And then the dark matter. These are fractions of energy density, so 27%. And then the baryons. It's interesting that these two numbers are not too different from each other. It's interesting that these two numbers are not too different from each other. We don't understand any of that, but that's all very interesting. Okay. Neutrinos we haven't measured, but we bound to be less than about that number. Squiggle in case that's not up to date. And we predict in the standard model, given our knowledge of neutrino mixing angles and such, that this number is greater than about that. So actually we're kind of within a factor of few of where we should see that. And then the photons, where we actually get all the information, is way down here. Okay, so that's the energy budget. We know these numbers at percent level now. These lectures are aimed at explaining this number.
Josh, is this your record?
Yeah.
Do you mind logging in and just also video streaming this part of the board? People are complaining about it too much.
Oh, which can it? Which is
on Zoom?
Do I have the link? Yeah, I apologize to people watching this remotely.
I think that part is covered by the other cameras.
Oh, no, yeah. Start video.
Yeah.
Okay. And then you can.
I-
Sorry. Okay. Looking at 5 screens. Okay. Okay. So some properties of dark matter. And again, you're gonna over the next. God, how long is the school? A month? Over the next month, you're gonna learn about all of these things much more precisely. But I get to say some of this first. Okay. So what is dark matter? It is dark. What does that mean? Well, it means that it doesn't have electric charge. More precisely, it's electric charge. If it does have electric charge, that's a small number. So I'll just say that. Okay. It's cold, so that Anne is teaching us about. But I'll just say roughly, if it's particles, then their velocity now is much less than the speed of light, or when structure formed. It is a more precise way of framing this in terms of free streaming length, but for now, let's just say it's cold. It's around now, so that means it lives a long time. It's stable. It doesn't have to actually be stable. It can decay, but it can't decay too quickly. So it's stable on cosmological timescales. There's very general bounds on it decaying to lighter stuff, that it needs to live longer than about 10 times the present age of the universe, 10 to 100 times, yes, it's about 10 to the 11 years. Otherwise, we change the Hubble expansion, so I'll just say these bounds are very general. If it decays into standard model particles, there are much more powerful bounds from it injecting energy that you would see in many ways that you're going to hear a lot about from world experts later on here. But let me just say, roughly speaking, it depends a lot on the details, but I'll just give it. So roughly, it's always about 1 million times more powerful if it's decaying into standard model particles, especially if they're not neutrinos. Okay, so this will be. Okay. If it's a particle, then we don't know its spin. We have basically no information about that, and there are models explicitly where the spin is 0, 1/2, 1, 3/2, 2. I'm not aware of any models past 2. I don't know. Maybe we can write a model past 2 today if you want. Okay. Now the mass. Okay. Well, if it's all one particle, there's a lower bound, roughly speaking, that it can fit within galaxies or astrophysical things that we see dark matter in. And that's going to be about 10 to the minus 22 electron volts. And that's where its de Broglie wavelength is about kiloparsec. Models that saturate this bound are called fuzzy dark matter. Only bosons can get that light. Fermi degeneracy places a bound of about a keV. Yeah, I guess I could write that. So it's 1 keV. The fermionic dark matter lives. So this region's only bosonic. Yeah, this is not the scale even log, I apologize. But at the Planck scale would be the heaviest that a particle can be, beyond which there would be black holes. We can even contemplate dark matter out here, primordial black holes or macroscopic things. But even just for a single particle, there's this huge range of masses, and there are models that populate this entire range. So we haven't made much progress there. Okay. And now you could ask, is dark matter all of one thing, or is it multiple things? So is it one or multi-component? Is it all WIMPs? Is it all axions? Is it half WIMPs and half axions? I'm going to kind of ignore that subtlety in these lectures and just pretend it's one thing, but you should always understand that to be just a simplification, and sort of any of the ideas I talk about for how dark matter can be populated can make some fraction of dark matter, and then multiple of these ideas could be relevant at the same time. So just always have that in the back of your mind, but otherwise I'm not going to say that anymore. It could be 100 different types of things. All we really know is the total energy density that they all add up to. Okay. Now, an important idea for certainly for the first 3 lectures will be the possibility that dark matter is what's called a thermal relic. This is roughly the idea that it had a temperature in the early universe that just like the Standard Model particles did. So dark matter thermal equilibrium, some temperature, which are called C dark, which need not be the same as our temperatures. And then the WIMP is an example of this idea of thermal relic. And in the WIMP case, you assume the dark matter annihilates, for example, into Standard Model particles. And then in this case, then the dark temperature would be the Standard Model temperature, so called T photon, but in general it can be different. And I'm going to talk about a lot of different ideas for thermal relics beyond just this one in these lectures. We don't know if this is just an assumption that we can look at the consequences. We don't know whether dark matter ever was in thermal equilibrium with other particles or not. Okay. So that's my primer. Any questions about anything I just said? Yes.
I'm just curious why nobody's looking at models that spin higher than 2.
Oh, yeah, and even hopefully I'm not wrong about that. The simple things that we know of all the way up to here, and then beyond there, it's a composite state, presumably, because you need a cutoff for 2 or higher, and then if it's a composite state in some hidden sector that you find that you might guess the lightest state will have smaller spin, but indeed that might not be true. So, but anything out here would naively be some strongly coupled thing that's complicated, and then you might guess one of these would appear first.
Okay.
But yeah. There's very famous things all the way down here, like Axion, Neutralino, some new vector, Gravitino. Okay. Any other questions? Okay. So now I start for real. Okay. So this will be our WIMP warm-up. Or really a sort of cosmic thermodynamic warm-up. I'll just review some things very quickly because I'm good already about the expanding universe. And then cosmic dynamics, which Jan also touched on. And I'll apply these ideas, which I don't run out of time. But these things I'm going to discuss first are going to be important both for the WIMP and for all the other types of thermal relics that we'll talk about in the next few lectures. Okay, so this I can do quickly because Anne did it, but some repetition. Never killed anybody. Okay. So if we just do GR and we demand a cosmology that's homogeneous and isotropic, then we get it FRW. Okay, and this metric is the following. And really the important reason to write this is to define a scale factor, which is useful to know about. And we got the cell angle. Okay. Okay. This is the scale factor. is normally normalized to be 1 today. So A 0 is 1. This is the curvature, and we know to a good approximation, at least, that the universe is flat. There's strong bounds in the curvature from the CMB, and the curvature grows less slowly than the other components as you go backwards in time. So when dark matter was produced, given the bounds now, it was irrelevant for basically all the mechanisms we're going to talk about. So for at least these production lectures, is a very good approximation. Is that K equals 0? I'm going to never talk about curvature again. Okay. Now, Anne mentioned this, but it's good to reemphasize. It's often helpful to think in terms of a co-moving coordinate. And that's just R here. And these are coordinates that do not expand with the universe. So if I talk about a fixed co-moving volume, that then its size in co-moving coordinates stays constant, but its actual size in physical coordinates grows. So the physical length call that R is going to now be time dependent. Scale factor times a co-moving coordinate. Okay, so I'll often talk about co-moving coordinates, co-moving volumes. We're going to be aiming, when we produce the amount of dark matter, at some number density per co-moving volume, and then I mean volume that's constant in this coordinate. Okay. We also heard earlier about the Friedmann equation. This is going to be. This just tells us that Hubble is driven by the energy densities in flat space. It's very simple, just up to a constant factor. It tells us that Hubble squared goes like energy density. I used the notation rho and was using epsilon, whatever. Okay, so this is mass. Hubble's mass dimension 1. Oh, yeah, and Hubble is A dot over A. So 1 over time, so it goes like energy. So this goes like energy. Okay. And then those omegas that I wrote before, now I can actually properly define it. It's the energy density of some component over what we call the critical density, which is just the total density in flat space. Yeah.
So the Hubble goes like energy. Could you help me out with that that dimensional analysis? How does that work out?
Yeah, did I screw up? Oh, why does Hubble go like energy?
I think, yeah.
Just as a time derivative, and then the A's can cancel, though I'm using A as dimensionless, but this way of writing it.
Okay, sure. And time goes like energy.
1 over time goes like energy.
Whatever time goes like it. Okay, thank you.
Yeah, for me, H bar is 1, C is 1, so, and Boltzmann constant's 1, and I'm gonna set many more things to 1. It's gonna drive me crazy. Okay. The critical density is the following: 10 to the minus 5 per centimeter cubed. Okay. Okay, good. And now, so I told you a co-moving coordinate, a co-moving volume will have constant size in terms of R, and that means it scales like A cubed. Okay, and then if you want to, you can sort of just use dimensional analysis to figure out how the different energy densities scale with energy. And went through this, but I'll just very quickly say, okay, so the energy density of photons, well, the energy of photons goes like the background temperature, and then energy density is energy per volume. So this scales as A to the minus 4. The energy density of dark matter. Well, now if it's non-relativistic, the energy is just the mass, which doesn't depend on the scale factor, which means that this scales as A to the minus 3. So you see, as the universe evolves, this falls more rapidly than this. Cosmological constant is, of course, constant. So then we can, just from this dimensional analysis, we can already predict how the universe should evolve. If I write the different rho, here I'll take gamma. So the radiation will fall the fastest. Let's take this to be the matter. Say this to be the cosmological constant. So this moment here, yeah, sorry, just label these. This is the radiation, photons. This is the dark matter. This is the cosmological constant. This is a terribly wrong picture. So. Okay, much better. So this will be today. Where the temperature 2 times 10 minus 4 electron volts. Now this moment is very important. This is what we call equality, which I'll label T equality. This is about 0.8 electron volts. So this is the moment where the energy density of radiation equals the energy density of dark matter. And you can think of that actually as a measure of the amount of dark matter. So if there had been more dark matter, equality would have happened earlier or later. You can move this curve up or down. So sort of the fact that the cosmology tells us when this moment happens allows us to extrapolate this curve back, and then that's the line that we're going to be targeting with dark matter production mechanisms. So to me, T equality is a measure of the amount of dark matter. And I'll draw one more line and say when MEV, that's where BBN happened. That's the earliest we really know anything, and beyond that, we're always just extrapolating, since BBN is the first moment where we have any direct information. So T equality, 0.8 EV, measures the amount of dark matter. And that's right around the energy scale where the CMB formed, and we don't have any fundamental understanding of why these two are around EV. There's a lot of scales in cosmology that could have been different that end up being similar, and that makes it actually a very confusing subject to me. Okay. Any questions about this expanding universe, which is kind of re-emphasizing things that Anne is doing more carefully and better? Okay. So this is when BBN occurred, and that's the sort of a event where we have information by looking at abundances of helium and hydrogen and so on, and we don't have any direct information about what occurred earlier than that. So we don't even really, we know that you were radiation dominated between equality and an MEV, and we don't even know, in principle, there could have been some earlier phase of matter domination. We don't know how high the temperature got. That's called the reheating temperature. The reheating temperature, say when you start everything, I guess that would just be here. This just has to be a number larger than 1 MeV. So we don't even know that the universe was ever hot enough for all the Standard Model particles to be radiation or not. All we know is that we had a radiation dominated universe at 1 MeV, and then we see things that happened after that. And before, it's all obscure. Okay. Any other questions?
Yes, I don't know if you can hear me.
Okay, so now I want to talk about cosmic thermodynamics, which really just means, say, the properties of gases of particles in the FRW metric. And this will be the kind of key technology that we're going to use to understand thermal relics like the WIMP.